Have you ever wondered what secrets lie beyond our solar system? Bill Nye recently revealed something that, honestly, sent shockwaves through the scientific community. Voyager 1 has detected 300 massive objects floating in the depths of interstellar space. After 45 years of exploration, this aging spacecraft continues to make discoveries that challenge everything we thought we knew about the cosmos. These aren't just random space debris. They're mysterious structures that could hold the key to understanding whether we're truly alone in the universe. Today, we're diving deep into Voyager's most mind-bending revelations. The genesis of Voyager's epic journey. Back in 1977, NASA launched what would become humanity's most ambitious space exploration mission. Voyager 1 and Voyager 2 were originally designed for a simple 5-year mission to study Jupiter and Saturn. But these remarkable spacecraft had other plans. The timing was perfect, a rare planetary alignment that occurs only once every 175 years, allowed the probes to use gravitational slingshots to reach the outer planets faster than ever before. What started as a modest exploration of gas giants evolved into the grand tour of our solar system. Voyager 2 became the first and only spacecraft to visit Uranus and Neptune, capturing images that, well, totally revolutionized our understanding of these distant worlds. The mission's success exceeded all expectations, with both spacecraft continuing to function decades beyond their planned lifespan. The secret to their longevity lies in their nuclear-powered systems and robust 1970s engineering. While their computers have less processing power than a modern calculator, their reliability has proven unmatched. Today, nearly half a century later, these cosmic pioneers continue transmitting data from the edge of known space, redefining what's possible in space exploration. Breaking the ultimate barrier. August 25, 2012 marked a historic moment in human exploration. Voyager 1 became the first human-made object to enter interstellar space. At 11 billion miles from the Sun, it crossed the heliopause, the boundary where our Sun's influence ends and the vast wilderness between stars begins. 6 years later, Voyager 2 joined its twin in this cosmic frontier, making them humanity's only ambassadors to interstellar space. The journey to this milestone wasn't easy. As the spacecraft approached the heliopause, they encountered a turbulent region where the solar wind collides with the interstellar medium. This cosmic battleground creates a protective bubble around our solar system, shielding us from the galaxy's harsh radiation. Voyager's instruments revealed that cosmic rays beyond this shield are 3 times more intense than within our solar system's protective embrace. The transition into interstellar space wasn't gradual, it was like stepping from a bustling city into a silent wilderness. The spacecraft's magnetometers detected the sudden change in magnetic field direction, while particle detectors registered the dramatic shift in cosmic ray intensity. This moment represented humanity's first direct contact with the space between stars, opening an entirely new chapter in our cosmic exploration. The mysterious humming of deep space. One of Voyager 1's most intriguing discoveries came in the form of sound, a low, persistent humming detected in the vast emptiness of interstellar space. This cosmic symphony isn't actually sound as we know it, but rather vibrations in the sparse gas that exists between stars. The discovery challenged our understanding of interstellar space as a perfect vacuum, revealing instead a dynamic environment filled with subtle activity. The humming represents the vibrations of electrons in the interstellar plasma, creating what scientists call plasma waves. These waves provide crucial information about the density and temperature of the interstellar medium, helping us understand the conditions that exist in the 99.9% of space that lies between star systems. The consistency of this humming suggests that interstellar space has a more uniform structure than previously thought. NASA's Nicola Fox emphasized the significance of this discovery, noting that no other spacecraft could have made such observations. The detection required Voyager's unique position beyond the heliopause and its sensitive instruments, which continue to function despite the extreme cold and radiation of deep space. This cosmic humming serves as a constant reminder that even in the apparent emptiness of space, there's always something happening. We just need the right tools to detect it. Defying death in the cosmic deep. Voyager's survival story honestly reads like science fiction. These spacecraft were designed to operate for just 5 years, powered by plutonium-238 that, gradually decays over time. As the radioactive fuel ages, it produces less heat, forcing NASA to make increasingly difficult decisions about which systems to shut down. Heaters that were meant to keep instruments warm in the -270°F environment of space, well, those were turned off years ago. Yet somehow, all 5 scientific instruments on both spacecraft are still functioning perfectly. This really defies all engineering expectations and, frankly, puzzles NASA experts who expected the instruments to freeze and fail long ago. The spacecraft's resilience truly demonstrates the exceptional quality of 1970s engineering and the conservative design philosophy that built redundancy into every system. The power situation gets more critical each year, with both spacecraft losing about 4 watts of power annually. NASA engineers are constantly juggling which systems to keep online, always prioritizing the most scientifically valuable instruments. Despite all these challenges, the spacecraft continued to transmit data across the 15 billion-mile void, with signals taking over 22 hours to reach Earth. This remarkable endurance has extended humanity's reach into the cosmos far beyond anyone's wildest dreams. The shape-shifting boundary of our solar system. The heliopause, which is our solar system's boundary, isn't the static barrier scientists once believed it to be. Instead, it's this dynamic, ever-changing frontier that actually moves and shifts like a living organism. Data from Voyager 1, Voyager 2, and NASA's Interstellar Boundary Explorer satellite reveal that this cosmic boundary creates unexpected angles and irregularities, really challenging our understanding of how solar systems interact with interstellar space. This discovery helps explain why Voyager 1 and Voyager 2 entered interstellar space 6 years apart, even though they were launched just weeks apart. The heliopause had shifted significantly between their crossings, demonstrating the dynamic nature of this cosmic frontier. Scientists observed the boundary moving at speeds that just contradicted existing models, suggesting that the interaction between solar wind and the interstellar medium is way more complex than previously thought. The implications are, honestly, pretty profound. If our solar system's boundary is constantly shifting, it affects how cosmic rays penetrate our protective bubble and influences the space environment around all the planets. Recent studies published in Nature Astronomy describe these findings as eye-opening, acknowledging that they challenge some fundamental assumptions about heliospheric physics. Future missions, including NASA's upcoming Interstellar Mapping and Acceleration Probe, will help scientists better understand this mysterious boundary. Electronic aphasia in deep space. In May 2023, Voyager 1 experienced what NASA engineers described as electronic aphasia. The spacecraft's attitude control system started sending garbled, incoherent data back to Earth. Like a person struggling to speak clearly, Voyager 1 seemed to lose its ability to communicate effectively, sending random patterns instead of meaningful telemetry about its health and status. The mystery only deepened when engineers realized that, despite the communication problems, Voyager 1 was actually functioning perfectly. Its radio signal remained strong and stable, which meant the high-gain antenna was still properly pointed toward Earth. The spacecraft's scientific instruments continued operating normally, completely unaware of the communication anomaly affecting their host vehicle. NASA's investigation revealed that the attitude control system had switched to a backup computer that had been dormant for years. A simple command to switch back to the primary computer resolved the issue, but the root cause still remained puzzling. Engineers suspect that cosmic radiation or maybe an errant command from another onboard system triggered the switch, highlighting the challenges of operating decades-old technology in the harsh environment of interstellar space. This incident demonstrated both Voyager's vulnerability and its remarkable resilience, proving that even after 45 years these spacecraft can overcome unexpected challenges. Cosmic IT support across 15 billion miles. Managing Voyager's computer systems presents some pretty unique challenges, honestly, challenges that make Earthbound IT support look, well, simple by comparison. These spacecraft operate with technology from the 1970s, including computers that have just 70 kilobytes of memory. That's actually less than a single smartphone photo. Yet NASA engineers regularly send software updates across the 15 billion-mile void, and, that process takes over 22 hours each way at the speed of light. The programming challenges here are immense. Engineers have to write code in assembly language, the most basic form of computer programming, because get this, the spacecraft don't have operating systems or any advanced programming tools. Every instruction has to be crafted to work directly with the hardware. which really requires intimate knowledge of systems that were designed nearly half a century ago. And the code, well, it has to be absolutely perfect. There's just no opportunity for quick fixes when the nearest technician is 15 billion miles away. These software updates aren't just, routine maintenance, they're actually lifesavers. Over the years, updates have fixed failing hardware components, optimized power consumption, and even activated backup systems when primary components failed. One critical update actually saved Voyager 1 from potential disaster by activating a fail-safe mechanism when a hardware component stopped working. This kind of cosmic IT support honestly represents one of the most challenging technical achievements in human history, and it's what's kept humanity's most distant explorers operational against all odds, revolutionizing our understanding of planetary worlds. Voyager's planetary discoveries, fundamentally changed our understanding of the solar system. Jupiter revealed itself as a world of extremes, with hundreds of massive storms, glowing auroras at its poles, and a complex ring system that's even more intricate than Saturn's. The Great Red Spot, which is a hurricane larger than Earth, had been raging for centuries, really showing us the incredible power of atmospheric dynamics on gas giant planets. Saturn's rings, once thought to be simple bands of ice and rock, turned out to be incredibly complex structures with thousands of individual ringlets and honestly, these braided patterns that just defied explanation. The discovery of spokes in Saturn's rings, those mysterious dark features that rotate with the planet, revealed that ring systems are way more dynamic than anyone ever imagined. But maybe the most shocking thing was the discovery of active volcanoes beyond Earth. Io, Jupiter's innermost large moon, displayed sulfur volcanoes erupting hundreds of miles into space, while Neptune's moon Triton showed nitrogen geysers erupting at temperatures near absolute zero. These discoveries proved that geological activity wasn't just limited to rocky planets, opening up new possibilities for understanding planetary formation and evolution. And most intriguingly, Voyager revealed that Europa and Enceladus likely harbor vast oceans beneath their icy surfaces, making them prime candidates for harboring extraterrestrial life. The Golden Record and humanity's cosmic message. Each Voyager spacecraft carries humanity's most ambitious message to the cosmos, the Golden Record. This 12-inch gold-plated copper disc contains sounds, images, and music representing Earth's diversity, including greetings in 55 languages and natural sounds from wind, rain, and animal calls. The record serves as a time capsule of human civilization, designed to survive for billions of years in the vacuum of space. Carl Sagan, who really spearheaded the Golden Record project, envisioned it as humanity's introduction to any extraterrestrial intelligence that might encounter the spacecraft. The record includes mathematical and scientific information, human anatomy diagrams, and cultural achievements ranging from Bach to Chuck Berry. It represents our species' optimistic belief that intelligence and curiosity are universal traits that could bridge the gap between civilizations. The Golden Record transforms Voyager from mere scientific instruments into cultural ambassadors. Long after their scientific missions end, these spacecraft will continue carrying humanity's message through the galaxy. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star, Gliese 445, potentially becoming the first human artifact to enter another star system. This cosmic message represents humanity's profound desire to connect with something greater than ourselves, embodying our species' eternal quest to understand our place in the universe. Legacy of discovery and future exploration. Voyager's legacy extends far beyond its original mission, inspiring decades of subsequent space exploration. The spacecraft's discoveries at Jupiter led directly to the Galileo and Juno missions, while Saturn observations inspired the Cassini-Huygens mission that spent 13 years studying the ringed planet. Voyager 2's brief encounters with Uranus and Neptune remain our only close-up studies of these ice giants, though, future missions are planned for the 2040s. Today, both Voyagers continue transmitting data from interstellar space, with NASA expecting to maintain contact until the late 2020s. The spacecraft will eventually fall silent as their power sources decay, but their journey will continue for millions of years. In about 300 years they'll enter the Oort cloud, and after 30,000 years, they'll leave our solar system entirely to orbit the galactic center. Current missions like Europa Clipper and the planned Dragonfly mission to Titan build directly on Voyager's discoveries, targeting the most promising locations for finding extraterrestrial life. the spacecraft's detection of subsurface oceans on Europa and Enceladus has absolutely revolutionized astrobiology, making these moons priority targets for future exploration. Voyager's story reminds us that the greatest discoveries often come from pushing beyond our intended limits, proving that human curiosity and engineering excellence can overcome any obstacle the universe presents. From detecting mysterious objects in interstellar space to revealing the hidden oceans of distant moons, Voyager 1 has fundamentally changed our understanding of the cosmos. Bill Nye's revelation about those 300 massive objects reminds us that even after 45 years, these remarkable spacecraft continue making discoveries that challenge our assumptions about the universe. As Voyager drifts ever deeper into the cosmic unknown, it carries with it humanity's greatest hopes and dreams. Thanks for watching Stellar Tech, and don't forget to subscribe for more incredible journeys into the mysteries of space and science. Imagine a moment when humanity's most powerful machine briefly created a microscopic black hole, a tiny tear in the fabric of space-time itself. This happened not in some distant galaxy but right here on Earth, deep beneath the Swiss-French border at CERN's Large Hadron Collider. In recent years, scientists have observed phenomena that could represent the birth and evaporation of micro-black holes, discoveries that challenge our understanding of physics, extra dimensions, and the very nature of reality. Today we dive into what happened after CERN scientists created these quantum black holes.
The machine that recreates the Big Bang.
The Large Hadron Collider at CERN stands as humanity's most ambitious scientific instrument, a 27-kilometer ring of superconducting magnets buried 175 meters beneath the France-Switzerland border near Geneva. Built between 1998 and 2008 through collaboration with over 10,000 scientists from hundreds of universities across more than 100 countries, the LHC represents the pinnacle of human engineering achievement. This massive machine accelerates protons to 99.9999991% of light speed, creating collision energies of up to 13 tera-electron-volts, conditions that haven't existed in our corner of the universe since moments after the Big Bang. The LHC's primary mission involves exploring fundamental physics through these extreme energy collisions, most famously leading to the discovery of the Higgs boson in 2012, which confirmed how particles acquire mass. The collider features 4 main crossing points where accelerated particles collide, surrounded by massive detectors like ATLAS and CMS that track the spray of particles created in these violent encounters. These detectors, built like giant 3-dimensional cameras made of millions of sensors, can capture the fleeting signatures of exotic particles that exist for mere fractions of a second.
The theory behind microscopic black holes.
The possibility of creating microscopic black holes at the LHC emerges from revolutionary theories involving extraspatial dimensions beyond our familiar 3. Models proposed by physicists Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, known as the ADD model, suggest that gravity might propagate through additional hidden dimensions, while other forces remain confined to our 3-dimensional space. These theories attempt to solve the hierarchy problem, why gravity appears so much weaker than other fundamental forces. A tiny refrigerator magnet can overcome Earth's entire gravitational pull, suggesting gravity's apparent weakness might result from it spreading through extra dimensions we cannot perceive. If these extra dimensions exist, they would dramatically lower the energy required to create black holes from an impossible 10 to the 19th giga-electron-volts down to potentially just a few tera-electron-volts. Precisely the energy range the LHC can achieve. Under these conditions, when protons collide at nearly light speed, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. According to Stephen Hawking's theory, such micro-black holes would be extraordinarily unstable, evaporating almost instantly through quantum radiation in roughly 10 to the minus 27 seconds while releasing distinctive particle signatures.
The hunt for quantum black holes.
The CMS and ATLAS experiments at CERN have conducted extensive searches for microscopic black hole signatures in proton-proton collisions. These searches focus on identifying the distinctive particle sprays that would result from Hawking radiation as micro-black holes evaporate almost instantaneously after formation. The CMS experiment completed comprehensive searches for microscopic black holes produced in high-energy collisions, analyzing data for the characteristic patterns these exotic objects would create. Their detectors look for events where particles converge inward rather than spray outward, consistent with space-time being warped by extreme gravity before the black hole's rapid evaporation. Recent Atlas collaboration research published in 2023 searched for quantum black holes in electron plus jet and muon plus jet invariant mass spectra using 140 inverse femtobarns of collision data. While no definitive evidence was found, the experiment set important limits on black hole production, ruling out their existence below certain mass thresholds in various theoretical models. The search techniques involve sophisticated pattern recognition algorithms that can distinguish genuine black hole signatures from the background noise of ordinary particle collisions. These advanced analysis methods continue to push the boundaries of what's detectable, bringing scientists closer to potentially revolutionary discoveries. Hawking radiation and instant evaporation. Stephen Hawking's groundbreaking 1974 theory predicted that black holes aren't completely black but actually emit radiation due to quantum effects near their event horizons. This process, which we call Hawking radiation, happens when quantum fluctuations create particle-antiparticle pairs right at the black hole's boundary. One particle falls in, while the other escapes. Now, for microscopic black holes, this evaporation process happens almost instantaneously. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. A micro-black hole created at the LHC would exist for about 10 to the minus 27th seconds, an almost incomprehensibly brief moment during which light can barely travel the width of a single proton. During this fleeting existence, the black hole would release its entire mass energy as a burst of particles, creating a distinctive signature that, in principle, sophisticated detectors could potentially observe. The evaporation would produce a specific spectrum of particles including quarks, gluons, photons, and possibly even some exotic particles not found in the standard model. This rapid evaporation ensures that any micro-black holes created at CERN would be completely harmless, disappearing long before they could interact with surrounding matter or, grow larger through accretion.
Evidence for extra dimensions.
The detection of micro-black holes would provide, honestly, the first experimental evidence for extraspatial dimensions, fundamentally revolutionizing our understanding of reality's structure. The Arkani-Hamed-Dimopoulos-Dvali model and Randall-Sundrum scenarios propose that our universe contains additional spatial dimensions beyond the three we experience directly. These hidden dimensions would be compactified, curled up so tightly at every point in space that we just can't perceive them in everyday life. Imagine for a second an ant walking along a garden hose. From far away the hose looks one-dimensional, but up close, the ant can move around its circumference through an extra spatial dimension. If gravity propagates through these extra dimensions while electromagnetic weak and strong forces remain confined to our familiar three-dimensional space, it would explain why gravity appears so much weaker than the other fundamental forces. The precise energy threshold for micro-black hole production would actually reveal the number and size of these extra dimensions. Recent theoretical work suggests that observing micro-black hole evaporation patterns could provide detailed information about the geometry of extra dimensions, potentially mapping aspects of reality that have remained hidden since the universe's beginning. This would represent, without exaggeration, one of the most profound discoveries in the history of physics.
The search continues with advanced technology.
CERN's search for micro-black holes employs, honestly, some of the most cutting-edge detection technology and analysis techniques that really push the boundaries of experimental physics. The Atlas and CMS detectors surrounding collision points contain millions of sensors arranged in layers, creating three-dimensional snapshots of particle interactions with unprecedented precision. Machine learning algorithms now analyze collision data, searching for subtle patterns that might indicate micro-black hole formation and evaporation. These AI systems can process vast amounts of data far more efficiently than human researchers, identifying anomalies that might otherwise be missed in the background noise of ordinary particle collisions. The CMS experiment's search for microscopic black holes has set increasingly stringent limits on their production, ruling out their existence up to masses of 3.5 to 4.5 TeV in various theoretical models. Similarly, Atlas collaboration research has pushed these limits even higher, with recent studies excluding quantum black holes below 9.2 TeV in the ADD model and 6.8 TeV in the Randall-Sundrum model. As the LHC undergoes upgrades toward its high luminosity phase, planned to begin operations in the late 2020s, the increased collision rate and improved detector sensitivity will provide even more opportunities to search for these elusive quantum phenomena.
Connections to dark matter and dark energy.
The potential discovery of micro-black holes at CERN could, really illuminate the mysterious dark sector of physics, which actually makes up about 95% of the universe's content. Dark matter and dark energy are still, among the greatest unsolved puzzles in cosmology, and we can only detect them through their gravitational effects on visible matter and the expansion of the cosmos. Some theoretical models even suggest that black hole evaporation might produce particles from the dark sector, which would offer us a unique laboratory window into these invisible components of the universe. If micro-black holes briefly connect our familiar matter with dark matter through quantum effects, then their evaporation signatures could finally reveal the nature of particles that have managed to elude direct detection for decades. Now, primordial black hole theories propose that tiny black holes formed in the early universe could account for some or maybe even all of dark matter. If CERN's experiments are able to produce micro-black holes with evaporation patterns that match theoretical predictions for primordial black holes, that would be honestly pretty compelling evidence for these cosmological models. Additionally, some theories suggest that dark energy's mysterious acceleration of cosmic expansion might be connected to extra dimensions through which gravity propagates. So, micro-black hole production could, in fact, offer indirect evidence for these connections, potentially solving multiple cosmic mysteries at once through a single experimental breakthrough.
Quantum entanglement and space-time connections.
The creation and evaporation of micro-black holes provides a unique testing ground for the revolutionary ER equals EPR conjecture, which was proposed by physicists Juan Maldacena and Leonard Susskind back in 2013. This groundbreaking idea suggests that quantum entanglement and wormholes, also known as Einstein-Rosen bridges, are actually the same phenomenon, just viewed from different perspectives. According to this theory, when particles become quantum entangled, they're actually connected through these tiny wormholes in the fabric of space-time itself. If micro-black holes form at CERN, their evaporation could produce entangled particles that reveal these quantum connections, potentially providing the first experimental evidence for this profound relationship between quantum mechanics and general relativity. Observing correlated particle decays from micro-black hole evaporation could demonstrate that space-time isn't really the fundamental backdrop against which physics happens, but rather something that emerges from deeper quantum information relationships. This would suggest that the fabric of reality is woven from quantum threads of information, instead of being a smooth, continuous medium. Discoveries like this could address the black hole information paradox, which is this really fundamental problem where quantum mechanics and general relativity seem totally incompatible at black hole boundaries. The data from micro-black hole evaporation might finally reveal whether information falling into black holes is truly lost, or somehow preserved in their radiation.
Safety and cosmic ray comparisons.
Concerns about creating black holes at the LHC have been thoroughly addressed through comprehensive safety assessments by independent groups of physicists all over the world. The fundamental argument for safety comes from comparing LHC energies with natural cosmic ray collisions that constantly bombard Earth's atmosphere. Cosmic rays from space carry energies up to 10 to the power of 20 electron volts, which is about 10 million times higher than the LHC's maximum energy of 13 tera-electron volts. These ultra-high energy particles create natural collisions with our atmosphere roughly 1 million times per square kilometer every year, and Earth has experienced this kind of bombardment throughout its 4.5 billion year history without any damage at all. If micro-black holes could pose any danger at the energies CERN explores, nature would have already conducted these experiments countless times throughout cosmic history. The fact that Earth and other astronomical objects remain completely intact demonstrates that such phenomena are either impossible or totally harmless. Even if micro-black holes formed but didn't evaporate through Hawking radiation, which would mean Hawking's theory is fundamentally wrong, they would still pose no threat, thanks to their incredibly weak interaction with ordinary matter. They would just pass right through Earth almost without effect, similar to the trillions of neutrinos that pass through our bodies every second, unnoticed.
The future of fundamental physics.
The potential discovery of micro-black holes at CERN represents a lot more than just confirming some exotic theoretical predictions. It would actually mark the beginning of a whole new era in fundamental physics research. Such discoveries would provide the first experimental access to quantum gravity, the long-sought theory that unifies quantum mechanics with Einstein's general relativity. Understanding how gravity behaves at quantum scales could, honestly, revolutionize technology in ways we can barely even imagine, maybe leading to new forms of energy generation, propulsion systems, or even manipulation of space-time itself. The knowledge gained from studying micro-black hole evaporation could also inform our understanding of the universe's earliest moments, as well as its ultimate fate. As CERN prepares for the high-luminosity LHC upgrade and looks ahead to even more powerful future colliders, the search for micro-black holes will continue with unprecedented sensitivity and precision. Every single collision brings us closer to potentially revolutionary discoveries that could reshape our understanding of reality's most fundamental nature. The journey into quantum gravity and extra dimensions is humanity's boldest exploration of the cosmos, probing the deepest mysteries of existence through the power of human ingenuity and international scientific collaboration. Whether or not micro-black holes actually exist, the search itself advances our knowledge of the universe's most profound secrets. CERN's quest to create and study micro-black holes really does represent humanity's boldest attempt to understand the fundamental nature of reality itself. Whether these quantum phenomena exist or not, the search has already pushed forward our knowledge of particle physics, extra dimensions, and those deep connections between quantum mechanics and gravity. As scientists keep pushing the boundaries of what's possible, we're standing on the threshold of discoveries that could transform our understanding of space, time, and matter forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more groundbreaking discoveries from the frontiers of science. Right now, 15 billion miles from Earth, humanity's most distant messenger is revealing secrets that are, honestly, rewriting our understanding of space. Voyager 1 crossed into interstellar space back in 2012, becoming the first human-made object to leave our solar system's protective bubble. But after a terrifying communication blackout in 2023, the spacecraft came back online with data that absolutely stunned scientists. The space between stars isn't the empty void we imagined. It's actually a dynamic, structured environment filled with cosmic weather, invisible boundaries, and phenomena that challenge everything we thought we knew about our galaxy.
The silent crisis.
April 2024 brought relief after months of cosmic terror. Voyager 1 had gone completely silent, transmitting only garbled signals that made no sense to NASA engineers at the Jet Propulsion Laboratory. After 46 years of faithful service, humanity's most distant explorer was dying. The culprit was a corrupted memory chip, likely damaged by a cosmic ray strike. The very phenomenon Voyager was studying had wounded it. Engineers faced an unprecedented challenge, performing brain surgery on a spacecraft using 1970s technology from 15 billion miles away, where radio signals take over 22 hours for a round trip. The rescue operation required rerouting code into backup memory areas, essentially giving CPR to a robot that predated most modern computers. By May 2024, the patient showed signs of life, with all 4 science instruments gradually coming back online. This wasn't just an engineering triumph, it was humanity's lifeline to the only measurements we have from beyond our solar system.
Magnetic mysteries beyond the edge.
The first shock came from Voyager's magnetometer readings after crossing the heliopause. Scientists expected some differences, but the interstellar magnetic field showed a dramatic misalignment compared to our sun's magnetic influence. This wasn't a gradual transition, it was a sharp boundary suggesting something far more significant than anyone had anticipated. The readings point to Voyager 1 entering a magnetic turbulence zone where galactic magnetic fields twist and reconnect in ways that could, honestly, reshape our understanding of galactic structure. These aren't small ripples in space, they're fundamental forces operating on scales larger than our entire solar system. The magnetic field orientations Voyager measures might even channel cosmic material into denser regions, potentially influencing where new stars form in our region of the galaxy. Each measurement reveals that interstellar space has its own magnetic weather patterns, invisible highways of force that guide particles across vast cosmic distances. The spacecraft continues to detect these magnetic anomalies, proving that the space between stars is far more structured and dynamic than anyone predicted.
The cosmic ray avalanche.
Crossing into interstellar space triggered an immediate and honestly shocking discovery. Voyager's cosmic ray detector recorded a sharp spike in high-energy particles accelerated to nearly light speed by distant supernovae and black holes. The increase wasn't gradual, it was abrupt, like stepping through an invisible barrier. This revelation exposed how effectively our sun's heliosphere shields Earth from the harsh radiation environment of interstellar space. We're living in a cosmic oasis, protected from particle bombardment that would be lethal to unshielded life. But the pattern isn't uniform. Voyager has detected systematic variations, suggesting natural radiation corridors, cosmic highways where particles preferentially flow. These measurements hint at larger galactic structures, possibly ancient scars left by stellar explosions that shaped our neighborhood millions of years ago. The spacecraft may be detecting pressure gradients that map onto invisible architecture spanning light years. Each cosmic ray measurement reveals more about the galactic environment, showing that we're not just measuring local conditions, but glimpsing the aftermath of cataclysmic events that continue to influence our cosmic neighborhood today.
Whispers in the void.
You know, the silence of space doesn't actually exist. Voyager's plasma wave instrument has completely shattered the old myth of cosmic emptiness by detecting these constant low-frequency oscillations that just permeate interstellar space. And these aren't just random fluctuations, no, they're structured signals, suggesting that the space between stars has its own unique acoustic signature. The instrument has even picked up multiple plasma density spikes, kind of like pressure waves moving through an invisible medium out there. Scientists think these could be shock fronts left behind by ancient supernovae that exploded thousands of years ago, still rippling through the interstellar medium today. So Voyager isn't just drifting through emptiness, it's flying through an invisible fog with its own distinct layers and properties. Some regions are hotter, others are denser, and together they create this complex three-dimensional structure that actually resembles weather patterns a lot more than the uniform void scientists once expected. This cosmic hum, it's really the background activity of our galaxy, a constant whisper from the space between stars. The plasma waves are revealing that interstellar space has its own dynamics, its own currents and temperatures, creating an environment that's far more active than anyone could have imagined.
Interstellar weather patterns.
Voyager 1 has actually passed through at least 2 distinct interstellar cloudlets since crossing the boundary, and this has revealed that the space between stars has structure, kind of like an ocean with currents and eddies. These aren't visible clouds though, they're regions where the plasma, dust, and gas density suddenly changes by factors of 2 or even 3 times. The spacecraft's instruments show evidence of these structured plasma ripples with clear boundaries, almost like atmospheric fronts out in space. NASA scientists now believe our sun is moving through the local interstellar cloud, and Voyager is helping to define its outer edges right now. This cloud exists inside the much larger local bubble, which is this enormous cavity created by ancient supernovae. These density shifts, they actually affect Earth's cosmic ray exposure over millennia. As our solar system drifts through different interstellar environments at 450,000 miles per hour, the radiation environment at Earth subtly changes, and that can potentially affect cloud formation and even mutation rates in living organisms. Voyager is showing us that interstellar space isn't just a straight path, it's really a gauntlet of invisible forces that create this complex, ever-changing cosmic landscape, complete with its own weather systems and boundaries.
Digital resurrection.
So, the 2023 communication crisis nearly ended humanity's only direct window into interstellar space. For months, Voyager 1 was transmitting incomprehensible data, its memory corrupted by cosmic ray bombardment. NASA engineers were suddenly facing one of their greatest challenges: remotely repairing a spacecraft that's actually older than most of their careers, and doing it with technology from the Carter administration no less. The solution took unprecedented ingenuity, rerouting decades-old code into backup memory areas while somehow maintaining all the critical functions across a 15 billion-mile gap. And every command took 22 hours to reach the spacecraft, so real-time troubleshooting was just impossible. The team basically performed remote surgery on a patient they couldn't see or touch. In April 2024, they finally had a breakthrough when basic telemetry resumed, and that was followed by the gradual revival of the scientific instruments. By June 2024, all 4 active science instruments were functioning again. This wasn't just an engineering triumph, it was humanity's lifeline to the only measurements we have from beyond our solar system's protective bubble. The rescue operation showed that even 1970s technology could be revived through innovative engineering, buying us precious additional years of interstellar data collection.
Mapping the invisible galaxy.
Voyager 1 is creating something, well, truly unprecedented, a navigational chart of interstellar space. With every data packet sent back, scientists are able to construct three-dimensional models of the Milky Way's magnetic and radiation zones, using Voyager's measurements as crucial anchor points. This, honestly, represents the first real-scale cartography of our stellar neighborhood. It's a bit like having a weather satellite, but for the cosmos. The cosmic ray gradients, particle density readings, and magnetic field orientations are revealing natural shields and danger zones, and these could really determine whether humans can safely venture beyond our solar system. The radiation environment that Voyager measures is far more intense than what astronauts face in Earth orbit, which makes these maps absolutely crucial for any future interstellar missions. Some astrophysicists even believe the structures Voyager is mapping may influence star formation patterns across our galactic region. Quietly, the spacecraft is drawing the first blueprint of the space between stars, creating detailed models that get refined with every new measurement. This mapping project has, well, become the foundation for understanding how to navigate the void between stars, potentially guiding future spacecraft through the safest corridors of interstellar space.
The protected oasis.
Voyager's measurements have revealed a profound truth about Earth's place in the cosmos. Our solar system exists within a protective bubble that shields us from an environment far more hostile than anyone realized. The dramatic increase in cosmic radiation beyond the heliopause demonstrates how effectively the sun's magnetic field deflects dangerous particles that would otherwise bombard our planet. This discovery reframes Earth not just as our home, but as our shelter in a cosmic storm. The interstellar medium contains radiation levels that would pose serious threats to unprotected life, making our heliosphere a crucial barrier against galactic hazards. Voyager's data shows that this protection varies as our solar system moves through different interstellar environments over millions of years. The spacecraft's measurements of density variations and magnetic field changes suggest our cosmic neighborhood is far from uniform. We're traveling through a complex landscape of radiation zones, magnetic boundaries, and plasma clouds that create an ever-changing environment around our solar system. Understanding these variations helps explain long-term climate patterns and cosmic ray exposure cycles that may have influenced life's evolution on Earth.
The eternal journey.
Beyond its scientific mission, Voyager 1 carries humanity's most enduring message to the cosmos. The golden record attached to the spacecraft contains sounds, music, greetings in 55 languages, and 116 images representing Earth's diversity. This time capsule is engineered for extreme longevity, designed to survive over 1 billion years in the harsh environment of space. In approximately 40,000 years, Voyager 1 will make its closest approach to the star Gliese 445, passing within 1.6 light-years of this distant red dwarf. Long after Earth's continents have shifted beyond recognition, long after human civilization has evolved or disappeared, this record will endure. Voyager represents humanity's most lasting trace in the universe, an ambassador that will outlive our species. No other human object will leave the heliosphere for decades, making Voyager literally our longest-lasting monument. The spacecraft transforms from a scientific probe into something more profound, a message frozen in time, carrying the essence of who we were in 1977 across the galaxy for eons to come. This cosmic time capsule gives Voyager significance that transcends its scientific achievements, becoming humanity's first tentative step into eternity.
Redefining reality.
The space beyond our solar system isn't the featureless void astronomers once imagined. Voyager 1 has revealed a dynamic structured environment with weather patterns, magnetic topography, and radiation zones that shape our galaxy's invisible architecture. The transition from our solar bubble to interstellar space isn't clean. It's messy, complex, and honestly pretty fascinating. Magnetic fields don't align as expected, radiation environments change dramatically, and plasma waves suggest constant activity we never knew existed. Voyager's discoveries prove that interstellar space has layers, fronts, and boundaries, creating a textured cosmic landscape far more intricate than anyone predicted. The spacecraft continues operating on borrowed time, with NASA making difficult decisions about which instruments to shut down as power gradually fades. Early 2025 saw the cosmic ray detector powered down to extend the overall mission, but 3 science instruments continue transmitting their faint 23-watt signals across the cosmic void. Each day, Voyager 1 operates as a gift of knowledge from humanity's only direct sampling of the space between stars, rewriting textbooks with every transmission from the interstellar frontier. Voyager 1 reached the other side, and the reality is more extraordinary than fiction. The interstellar medium isn't empty. It's a structured, dynamic environment that challenges our understanding of cosmic architecture. From magnetic mysteries to plasma whispers, from radiation avalanches to cosmic weather patterns, Voyager continues revealing secrets that rewrite astronomy textbooks. This incredible journey proves that sometimes the most profound discoveries come from the simplest act of reaching beyond our boundaries. If you love real space exploration without the hype, smash that like button and subscribe to Stellar Tech for more mind-blowing cosmic discoveries. The universe is far stranger than we thought.